So the idea now is to introduce a bit the basics behind what we call smart cloud methods, because I thought before I talk about material point method, which essentially is in the book that we just published with Nguyen Vinh Phu, that I'll give you a reference to, it would be nice also to tell you about some of the new things we've been doing on adaptive point collocation methods, so adaptive clouds, what we call smart clouds. And so I will first really relatively quickly motivate the problems that we're interested in, which are called free boundary problems. Because, well, free boundary problems are really everywhere in nature, and I want to give you some examples of that. Also because it's a problem close to my heart. I started working on that during my PhD, and I've not stopped since then. So this is, I think, very, very useful. And because I want to also give you a hint as to where I work, which is now here for 10 years at the University of Luxembourg. And this is where, more or less where I live. In fact, you can see where I live on the hill at the right-hand side of the screen. This is where my house is located. And the university is this big L-shaped building, inverted L, or maybe you can think about it as a cross. And you see around it all the steel works. So it's really an interesting place. And there is, in fact, a sculpture which is done by an artist, which took part of, let's say, the sounds in China and moved them back to Luxembourg, because the idea is that one of these high furnaces to make steel was dismantled here and shipped to China and then rebuilt in China. And what they did is that they put some microphones and some recorders in the Chinese village where this was moved. And then they transferred the sounds to Luxembourg. So when you walk there, you can hear the sounds of the village, at least when the sculpture is working. And this is really a very nice connection, I think, that we have here. It's quite beautiful. And okay, so that's basically the campus. It's a super dynamic place, so I highly encourage you to try to visit me. There are lots of visiting programs. We could also think of China Scholarship Council, and I would be very happy to visit you as well in where you are, because it's very important for me to build this collaboration further. So this is also Luxembourg. It's the city center down close to the river, very beautiful place. It's a medieval castle as well that you can see. This is the place, so it's in between France, Belgium, Germany, and it's very exciting because you have, for example, Schengen, which is where you get the visa from when you go to Europe. Well, this is close to here, and it is at the triple junction between three countries, which is quite unique to Luxembourg, and I think it gives it a very nice flavor, very international flavor. And if you compare, that's the Paris region where I'm from. This is called Île-de-France, which means France island. And it is 17,000 square kilometers, very small compared to China, obviously, and to any region in China. But if you look at Luxembourg, it's 2,500 square kilometers. So it's about 5 times to 6, or even 6 to 7 times less, 7 times less than the Paris region. So it gives you an idea what sort of scale these things are. Very small country, very dynamic. And you can see the team a long time ago. Now it looks quite different today, but still, it grew in size. We were at some point 35 people in the team. And so I'm very, very glad that you can see people from everywhere, from Vietnam. You can see people from France, from Iran, from Italy, from Iran, from Dutch guy, Lars, from Italy, again from Iran, from France, from Jordan, from UK, from Latvia, if I'm not mistaken, from India, from Greece, and from Mexico and Canada at the same time. So you see people from everywhere. Okay, so this is why Luxembourg is so exciting. I would definitely encourage you to come. I mean, again, I extend my my invitation to you. Okay, so what are free boundary problems? So first of all, I want to give you two examples throughout the whole lecture. The first one is not wind turbines necessarily, but fracture mechanics, stress analysis. Give me a component, I want to give you what the stresses are. Basically, that's the question. And of course, it could be applied to acoustics, it could be applied to any problem that you're interested in. And on the right-hand side, give me a brain that I want to cut. This is the brain when it's being, open. And then the surgeon needs to do something about it, So it tells you when you see that the complexity of the type of operations we're talking about, because if you don't know anything, how in the world are you going to do this, right? So what are free boundary problems? That is what we are interested in. So free boundary problems are solving partial differential equations, PDEs, in a domain, a part of whose boundary is unknown in advance, and that portion of the boundary is called the free boundary. And this was written by Avner Friedman in year 2000. So interface problems, they appear totally naturally. So why are we interested in interface problems? This is the name of my team, legato. This is a term in music. When you link up in Western music, you link the things up together. So this is different from staccato. So for example, if you sing la, 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 this is linked. If you sing la, 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 this is staccato. This is separated. All the three different notes are played differently, separately. So if you, again, I like these little diagrams with 2 dimensions. So you can see on the right hand, on the top, on the vertical axis, discontinuities. So as you go up, the discontinuities increase, and as you go right, the scale decreases. And the question is, what is going on? So if you look at an Airbus, or if you look at a car, if you look at the brain, then what you see is that these things are totally continuous. From far away, they look like one piece of material, like a potato. It looks like one piece. It doesn't look like all the constituents. Obviously, if you zoom in the car, this is a project with Bosch, which was very interesting. I'll tell you about it if you'd like, on printed circuit boards and solder joints for my PhD student Alex Menk. Or if you look at the Airbus A380, you see all these very intricate layers of composites. Or if you look at the brain, if you zoom in, you always see that something is going on. So you see discontinuity. So if you keep zooming down, at some point things will become discontinuous. You will get to the atomistic level, and then things become continuous again because you're talking quantum mechanics. So you're talking about strain energy density functions. And you're talking about energy potential and so on. But of course, in the meantime, you have discontinuities to deal with. So this is what happens at the top here. You have this little solder joint. So the solder joint has 1 grain, 2 grains, 3, 4, 5, 6 grains here. It's very coarse solder joints. At the interface, you have a jump in strain. Why? Because you have a different material on the left and on the right. So these materials being different, you, of course, have different material properties and therefore a jump in the strain field. And you have a continuous stress, right? And you have a discontinuous displacement. Same here, if you have a continuous displacement because there is no crack, but here you have a crack, therefore you have a discontinuous displacement. So these discontinuities, they are very important. And I know that you guys are teaching XFEM, so you're very well aware of the importance of these discontinuities. Okay, so if you look here at the carbon fibers, you see a discontinuity across the carbon fiber and the matrix, and so on and so forth. So all these things are very well known. And now if you cut through a brain tissue, you will get a discontinuity here, which hopefully you don't need to mesh because it's easier not to mesh. So this is what we call free boundary problems. And again, if you go from the legato, where you sing all the notes in a linked way, in a very smooth way, different from staccato when you go at the small scale, when it sounds a bit like this with little jumps and discontinuities between the words, you see? So that's a different way to see things. So what we do basically is, this is a very nice concerto, which I really like, by Brahms. And if you think about what we are basically doing, we are orchestrating the sound of materials. If you go lower, you see staccato. If you go higher, you see a very smooth thing. So if you are listening to the material at the coarse scale, you would listen to something very smooth, but at the fine scale, you would hear very disrupted sounds with very many jumps. So there are many examples, multi-phase, you have fracture of concrete that you have here, you have here the problem of multiple bubbles that are created, non-Newtonian fluids here, and some sort of dam break example here. So lots and lots of different examples. Just after my PhD in 2015, I worked with Zhao and Dudu and Q on the problem of nanophase, let's say heterogeneities, where the problem was to find the optimal shape for these nano shapes, because they will optimize the energy density inside the domain and outside, as well as the surface energy, because we're talking about a nanomaterial, and the nanomaterial happens to have a very high energy on the surface, which is why you don't get a sphere as an optimal shape, but a shape which will also take into account the length of the interface, not only its surface area. Another example we're interested in is the keloid, which is a scar between healthy skin and non-healthy skin, which is a keloid scar. Very similar to cancer in many ways due to inflammation, we believe, and we have experiments going on with biologists at the moment trying to figure out how these keloids grow and why. But as you can see, there is an interface between the keloid and the healthy skin, and it grows over time. This is another example of what we are interested in. And we have a weak discontinuity. Another example, and so the key point here is to try to figure out what is the growth of this biofilm. So on the interface, you will have a velocity potential, and that will have a gradient, and this gradient is going to push the material outwards, for example, right? So this is going to be the bacteria growing and pushing outward. And so outside in the water phase, we have a Laplace equation, and we have a Poisson equation in the bacteria phase, right? Okay, so now the problem is, when do free boundary problems occur? So, of course, fracture mechanics, Taiwan earthquake, fragmentation of concrete, landslides in Colorado, lots of examples of fracture, like the Comet aircraft, which became a convertible aircraft, but it was not foreseen. A problem of fracture in biomechanics, and so on and so forth. So fracture is really everywhere, and what I show today are simple examples of what you can get free boundary problems with. For example, here, needle insertion inside the liver to try to deliver a seed to a cancerous tumor. And here you have solder joints. In the middle, you have fracture of a concrete beam, and here at the bottom left you have a smart cut phenomenon with hundreds of cracks growing using XFEM. This is the work of Dana Sutula, which is really amazing work, and work with Lisa Cahill in Limerick at the bottom right, where you see the propagation of cracks in composite materials. So and of course the work of Xuan Peng, who did his PhD with me, and Elena Troshenko on propagation of cracks using isogeometric analysis with boundary elements, which is one of the best work that we've ever done, I think. Okay, so now, first example, cracks propagating inside a domain. So you would like really to figure out what exactly is going to happen, what is the most energetically favorable growth of crack that we can do in one increment. So, you know, you do a global minimization on all the crack tips, and you try to compute which crack should grow. And as you can see, it starts here, but then at some point, the most optimal crack is not here anymore. It starts to grow next to it. and so on and so forth. It's a very complex problem to solve, and Dennis did that very simple MATLAB code, well, not so simple, but very beautiful work that he did. Again, cutting in soft tissue that I've already talked about today. And the discretization. So now what is it about discretizing moving boundary problems, and why maybe do we need mesh-free methods or collocation methods or similar? So first of all, what we can see at the top is what happens in finite elements. So in finite elements, you have these interfaces that grow, right? And these interfaces maybe merge together. But as you can see on that picture, the mesh is conforming to the interface. So you see the mesh is always following the interface. So this is called conforming meshing. On the right-hand side, you see a crack, and the crack is moving with this little roses around there, which is fixed, but moves itself is fixed, but it's being attached to the surrounding mesh. So this is beautiful, but it's also very costly, in particular in terms of remeshing. And it's sometimes almost impossible to remesh in 3 dimensions with all these cracks propagating and coalescing. You can imagine the complexity, because you get very small elements, and generating these meshes is not feasible in finite time in general. So we cannot know. So that's why people came up with partition of unity methods. The book that we released, we will release in October with Sundar in IIT Madras. And what we see there is that the mesh is independent from the growth of the interfaces, because we can include discontinuities and singularities in the approximation field. So that's been quite a big advance in the last century. So now there are really 2 approaches to handle interfaces. The first approach is use, let's say, a coupled approach. So what you want to do is you want to couple the mesh with the geometry. That's step 1. What you want to do as a second approach is the opposite. You want to decouple the mesh from the geometry. And that is quite interesting, because at the end of the day, it seems like you have 2 approaches that are opposite to each other to solve the same types of problems. You see? So now, how does that work practically? Because you would say, in one sense, that you would like to keep the same representation from the geometry and for the simulation, so that would be something like isogeometric analysis. On the other side, you want to decouple, so you want to have the mesh which is independent from the geometry. So these 2 approaches seem to be totally opposite. So what we're going to try to address today and now is, what are the better approaches? What is the better approach? Of course, there is no general answer to that question, because if there was a general answer, there will be no research. And when should we go for one, and when should we go for the other, and what is the role that finite differences can play, meaning collocation methods. Collocation methods are not hugely popular, except for boundary elements maybe, but in terms of more general collocation schemes, they are really secondary approaches. So we try to rejuvenate them, and we wrote a few papers on the tutorials for these topics. If you're interested, I can give you the list. In fact, it was in the bio that I sent earlier. Okay, so now let's see what we can do. So now, there are 2 approaches. Let's see what generalized finite difference methods can do. So what are these generalized finite difference methods? So if you go back to the literature, you see 1953 already, and 1960 with McNeil, Forsyth, and then Frey 1978, Jensen 1972. And the idea is really to use Taylor series expansion to obtain finite differences. And using that, you try to approach the derivatives of the operator, right? So you have an operator, it has first, second, third derivatives in time, space, you have Laplacian, you have different operators, and you want to look at these operators in terms of their numerical formulation. And you want to approximate the operator, different from finite elements, where you want to approximate the field, the unknown field. It's quite a different idea. In one case, finite differences, you approximate the operator. In the other case, you approximate the unknown field. Very different problem. At the end of the day, it boils down to the same solution in one dimension. You get the same equations, but the approaches are totally opposite to each other originally. And the idea is, how can we, we can easily imagine calculating a derivative by looking on the right, looking on the left, doing the difference, and divided by the length of the interval. That would be an approximate of the derivative. So, of course, this is possible, but now let's imagine that you are in 2 dimensions and that the points are totally irregularly placed, maybe using a finite element mesh. Then how do you do it? So this is called generalized finite differences, and there are some papers that work on this. And the question is, how do you compute the operators? And that's what we will see in a few slides. Now, why really use strong form methods? Because these types of methods are known as strong form because you immediately, directly write the partial differential equation you're interested in at all the points in the domain that you want to solve it at. So you say, I have Laplacian plus b equals 0 here. So I compute the Laplacian locally. It gives me an operator. I put that on a row of the matrix. I compute b of u. I put that on the right-hand side. And that gives me the operator I need. That's it. So this is quite straightforward in general, at least for linear problems. Now, what about the approaches that you can use in order to write these operators? Right. So this is really the different. There are different questions. So, for example, you could use radial basis functions. So, in that case, what you do is you say that, okay, you assume that you have a cloud of points, and they are used as a basis to build radial basis functions. And these radial basis functions are then used to compute the derivatives in question. Right. So, what you say is a bit like a Galerkin method. You substitute the radial basis functions, and then you use the Kronecker delta property to end up with the equations at each node. That's an approach. Okay, and then there are some mathematical results about this, but needless to say that having a mathematical approach to point collocation methods is extremely difficult. So there are different approaches. The first one is to have a finite difference stencil on irregular centers, and to use a polynomial least squares method, for example, Benito. And this is known as local collocation. Second is you use radial basis functions, which seems to be better for irregular data than local polynomial least squares, right? With, of course, some disadvantages of RBF. Then generalized finite different methods will allow a lot of flexibility in the choice of stencil supports. Although RBF and GFD are not developed as much as the polynomial methods, of course, because polynomial methods are very easy to use. You can build polynomials very straightforwardly. Okay, so that's basically that. And then about RBF interpolation, you have different choices for that. So you have conditionally positive definite functions, multi-quadratic inverse multi-quadrics, Gaussian Wendland C6, and so on. So there is always a trade-off between the accuracy of the interpolant and the scaling parameter, because you would like to have small scaling parameters so that you can remove, the large bandwidth of the system matrix. But you also would like to have smooth solutions that are stable. So you would like to have a scaling parameter which is as large as possible, but still have a numerically non-singular RBF matrix. And that is the art. And I highly recommend that you read the papers by Davidov, D-A-V-Y-D-O-V, because he is one of the world leaders in that area. And recently with Pratik Suchde from my team, they wrote a review paper on how to place the centers of collocation methods in general and how to optimize the point placement. And this review I think is outstanding. So I highly recommend it, as well as the work of my PhD student that I will show you later. Okay, so what are collocation nodes? So we have collocation nodes are here. So, okay, that's one point, xc. You have a radius, rc, and you have a field point, xp, that are also known as particles. And the support is this area over which, or the volume over which the point xc has an influence. And so the question is, okay, what would you like to do? Well, you want to compute the derivatives at xc, which can allow you to reproduce the field values at each particle pi of the collocation node support. Okay, so basically you want to compute all the field derivatives here, which allow you to compute the values at points pi. Okay. So what is a finite difference method? Well, that's what we said before. All we do is we write at xp at any point, right? That is here. We write the value as the value at xc plus some corrections that come from Taylor series expansion. What else can we do? I mean, it's the very logical thing to do. If you assume the solution is smooth, very important point, then you know you can do that very easily, and there will be some convergence radius of the Taylor series expansion and so on. So you know that you will eventually converge if the solution is smooth, and only if it's smooth. If you have a very strong gradient, then the collocation method from that standpoint will not work, because you have a Taylor series expansion, which is a polynomial function trying to approximate a jump or a singular value, a singular function, and of course we know that doesn't work, and you are facing with the problem of Gibbs phenomenon. So this is not what you should do. Okay, so now let's imagine that you use a second order approximation. If you use a second order approximation, you'll see that you have first derivative with respect to x and then y, second with respect to x, second with respect to x and y, and second with respect to y. If f is smooth enough, this one is the same as dy dx, so there is no issue there. Now what we can do is, for a support composed of 5 particles, so remember what the particles are, they are here, so let's say 1, 2, 3, 4, 5, we have 5 particles in the support, we can write 5 equations. xc, c is the center, it's the collocation point that you're interested in, so you just write the Taylor series expansion for each and every derivative that you're interested in. Okay, so then if you do that, you write this times this, plus that times that, plus this times that, and so on, will be equal to f of xp1 minus f of xc. So what you essentially do is, for each of the points, p1, p2, p3, p4, p5, you write the Taylor series expansion, which gives you f of xp1 equals f of xc plus the corrections due to the derivatives, and you do likewise for all the other points. So now you can see that if you have 5 particles, you can write 5 Taylor series expansion, and therefore you can hope to find 5 values for these derivatives, because that's what you're looking for. After all, what your question is here is, what is the derivative of function f at point xc? What is the with respect to x, then with respect to y, with respect to x twice, and then x and then y twice. So that way you have an approximation of this. So this is what you do. You put that in matrix form. You invert the matrix. You hope that it's invertible. Of course, that would be hopeful. And that's what you get. So now the problem is that in the previous case we had exactly 5 derivatives and exactly 5 points, but that will never happen. I mean, usually you will have cases where you either have too few points, in which case you can't do anything, or too many points, in which case you can do something, but the system is overdetermined, And of course, you cannot solve it exactly, but you can solve it in the least squares sense, which essentially boils down to doing it this way. So now what you do is you have a least squares functional that you're writing, and you try to minimize that with respect to the parameters. Okay, so so far so good. That's the very usual way of doing things. Now there is a second approach which is maybe unfortunately not very well known, and which is known as the discretization corrected particle strength exchange. So I have to say that the first time I heard this, I thought that was a mouthful, because it's quite complex to even read, needless to say, to understand, but there is a lot in that method, and I will try to tell you a bit about it, because I'm almost sure that you probably didn't hear about it. And if you like, I can also give you the papers, because they, I think, are quite useful. So let me start from the beginning. So what we do here is that it's exactly the same as before. So we try to identify the value of the derivatives at a point xc. So it would be like that one. We try to get the fh, the x. We try to get, of course, the value of the function, the first derivative with respect to x, with respect to y, partial x, partial x, partial x, partial x, partial y, sorry, there's a typo here, and partial y, partial y. All right. Okay, so now what we do is we write it now as some sort of integral, right? Instead of writing it as a simple sum. So then we end up with some sort of, let's say, moment matrix, Mij, and that moment matrix we use directly in order to identify or to compute the coefficients that we need. Okay, so basically we did exactly the same as before, except that we are now correcting with an integral value, right? So this is the basic idea. And on that topic, I recommend that you look at the work of Ivo Balzarini at Max Planck Institute in Dresden, because he is one of the world leaders in that area. He came up with the idea with his PhD supervisor, and he's really an excellent guy. Okay, so once we have selected the appropriate function, because basically we have a smoothing function, which is this kernel here, we can apply the desired derivative, and we just set all the moments to 0 except the one that we are interested in, which we set to 1, and we do that alternatively. So first we set the first moment to 1 and the others to 0, and then we set all the other, the first to 0, the second to 1, and all the others to 0, and so on. And that gives us essentially a set of equations which we can solve. But first we need to have a weight. So again, like in mesh-free methods, we have exponential weights, third-order spline weights, or fourth-order spline weights. We can use different things, and of course they all have their own advantages and drawbacks, which I identified in the papers as well. And that's it. So now we are going to look at a few problems using this discrete correction particle strength exchange. Just to let you know, what we have managed to do is to have an adaptive point collocation method. So this adaptivity allows us to optimize the point placement based on an error indicator. Okay, so similar to what I was telling you, if you remember, about the surgical simulator, when we were trying to identify what would be the best mesh for the system, this is something that we are interested in here as well. We would like to have the optimal point distribution in that case. And I'm really encouraging you to look at the papers that I will give you, because they will allow you to understand better the way we do it practically. So the first thing we remark by solving the problem, so here we're solving a very simple linear elastic problem with internal pressure in a sphere. Well, you know what I mean. So basically we're doing that, and we're computing the stresses, and we're doing that on a code which is parallel, and that's also available if you're interested. And we are looking at different values of the weighting function. So you know, either a third order, fourth order, or a linear function. So what we see, linear function, the error on sigma 1,1 is constant, and we cannot decrease it by changing the power parameter. But in the other cases, we can see in particular for the fourth order spline that we're getting better results than the others. So this is what we therefore used. And the thing is that depending on each case, that was generalized finite differences, and now for DCPSE, well, you see that you have some sort of optimal shape parameter, which is given here, which will give you the minimum error, and then if you increase it too much, the error increases again, and if you choose it too small, the error increases again. And you see that this optimal parameter is about 0.3 to 0.4, at least for this particular case. Again, if we compare polynomial basis to exponential basis, what we see is that we have much better results with the polynomial basis, up to 1 order of magnitude less, even 2 orders of magnitude less error, which is great. So it's basically, sorry, it's the opposite. Polynomial basis better than the exponential basis. And we still don't know why, but that's what we see. Now, if we look at the support size on the boundary, because this is a very important question, what happens close to the boundary? In mesh-free methods in general, a lot of people are avoiding the problem. But you know, even in Galerkin mesh-free methods, you have this support that intersects the boundary. And when that happens, you lose the Kronecker delta property on the boundary, because you basically lose everything in terms of you do not have a zero test function on the boundary anymore. So this is something that we need to take into account. Okay, so that's that. Okay, so now what can we do with that? So let's look both at Voronoi diagram GFD, so where we have generalized finite differences, and the points in the generalized finite difference are distributed using a Voronoi diagram, which is a very well-known and approach which is dual to Delaunay triangulation, tessellation. If you have more nodes than derivatives, you need a least squares approach, and the contribution of each node in the fit only depends on the distance between the reference node and the support node. And the Voronoi diagram can be used to add geometrical information, right? So in DCPSE, if more nodes than derivatives, there is a least squares approach, and the contribution of each node is in the LS fit only depends on the distance between the reference node and the support node, and the Voronoi diagram can be used. But we use a convolution, an integral, discrete sum, weighted by area, and not simply unity. So this is what DCPSE changes. So let's look at how it looks. This is a Voronoi diagram, reference node and support node. So if we use a Voronoi weight as opposed to a simple weight, we see, well, basically that there is almost no difference. So this is reassuring, so which means that there is probably no need to be doing these changes. Okay, and now those are the results with mesh convergence, which is a hard topic because there is no proof of convergence for such methods, so we can only hope to get things as beautiful as finite elements. Let's look at efficiency. So we have different methods here, and we try to look at the convergence rate in terms of the L2 weighted average. And the convergence rate actually is not that bad because it's actually close to what we would expect in finite elements, which would be 2. But here, for that problem at least, So you see that in terms of the time to compute, there are different methods that we tested: interpolation, MLS, RBF-FD, DCPSE2, and GFD. What we see is that clearly the convergence rate that we get, which is one of the best, is DCPSE2, and we get a computational time which is significantly less than IMLS, which actually is half. It's better than generalized finite differences, so clearly it seems like DCPSE is the method to choose. And yeah, so now if we let's look at some conclusions. So first of all, we need a sufficiently large support, but also not a too large support, because otherwise we end up with a huge bandwidth, and this is not stable. Well, and this is also time consuming in terms of memory. What we see is that we need 11 to 15 nodes for 2D problems and 37 to 45 nodes for 3D cases. And we need, let's say, a large number of nodes to get proper simulation. Okay, and what does it mean in practice? So if we look at this flange here, we assume there is uniform pressure loading here, displacement constraints there, here, and there. And now the question is, what is the deformation of this? Again, we started directly from a CAD file, so from NURBS, which was discretized using two approaches. So one was an STL file, which is basically a triangulation of the surface, and the other was simply putting collocation points along the splines using the splines directly without any mesh. And I think that's also very, very nice. And the third was to embed the whole flange into a regular lattice of points, so that we don't even need to know where the points are. And we just then add the points on the boundary as needed. I will talk about it a bit later. Okay, so now we look at the results using generalized finite differences, that they look like that with a very nice stress concentration. And now I'm telling you what we are working on. So although now most of the results are in the recently published papers that I was mentioning. So let's imagine that you have a structure to look at. So for example, this little bunny. This little bunny is, of course, relatively a simple shape in that case, but it could be, of course, a much more general shape. And the idea would be, okay, can we simply have a general regular mesh, and can we put some points which are either in or out, and then work on imposing boundary conditions. So first we impose the Dirichlet boundary, then we impose the Neumann boundary, if you can see the points that are here at the interfaces, intersection points that I just created. Then we impose maybe the Neumann condition, so we need some more points along that surface, which is known maybe by NURBS. And what we are now able to do is to do all this for very generic problems. Of course, you will have some regions where you have problems. So for example, here you can see that you have a cusp inside this element. So of course, you will not even see the difference here. You will have only one material inside that box, and you will not be able to solve it. So what you, of course, can do in these problematic regions is zoom in. And once you have zoomed in that region, you will simply add points at the interfaces, at the intersection between the geometry and the mesh. And that's it, basically. Then that will allow you to have a better description of the boundary. And we do that in a semi-automatic way, let's say. So same here, we will have to add some points which will allow us to take care of the boundary. Now we don't have of course we are not able to handle a kink, because that will create stress concentrations, and we can expect that we need here some more points. And again, the paper by Pratik Sushde and Oleg Davidov is talking about this very nicely. Okay, so now there are some references, in particular from Davidov and Hoan and others, that are very, very useful. Some references by Benito on how to compute DCPSE. So I can give you those references as well as the presentations if you are interested. I think it's very worthwhile reading this. In particular, that paper with Owen and Davidov, because that will give you quite a number of ideas. So what we do is, from an STL file, we embed the STL file inside the domain. We cut everything that's outside, and we look at the convergence. So here we look at energy, Cartesian, symmetric, and so on. So we look at all the different convergence rates, and you see essentially the results is that the convergence is in the L2 norm of slope 1, which is what you would get. So you would expect 2 in the L2 norm, and you get 1. As you would expect 2 in finite elements, so here you get 1, right? So this is something that you need to take into account, right? Again, if we use different approaches, we see the convergence rate on that curve. Okay. So in terms of number of nodes, we can compete with finite elements. So you see finite elements here, collocation here. So in fact, the slope is a bit smaller, but not much. And for the Cartesian case, we get a higher error, but the slope is approximately the same too. Then we dealt with these very nice problems of a chair. Again, this is done with open source codes like open source Elmer, Codaster, and FreeCAD. And we have different materials here, and we have different nodes and tetrahedral elements and so on. So it looks like that. You have about 1 million elements. And we are comparing all 3 solutions between what we're doing and the different solutions. So yeah, if you look at the cut view of the distribution on the seat, you see that there is barely any difference. If you compute the von Mises stresses, you see that there is quite a good distribution. And yeah, and finally you see this. This is basically a wind turbine blade that we were working on, and we definitely need adaptivity, and this is something that I would really like to talk about, because this is a problem which is, first of all, close to my heart, because I've been working on it like for really ages. And I think adaptivity, in fact, I will show you the paper later if you are interested, but essentially adaptivity will allow you to, let's say, optimize the mesh and the point placement given an error level. And again, here we always assume that we do know that the problem that we are solving is the right problem. So we are not asking the question, is it the right problem? We're just saying, this is the right problem. Are we solving it right? Are we solving it precisely enough? Okay? So that's really our main challenge. And so how do we deal with error estimation? And I will come back to that at some other time this week. I just want to tell you for now that we have worked on that with a company which is a research center called Senairo, and they have implemented this in their commercial version for 3D fracture mechanics. So you see how a crack can propagate, and it's actually decimating the number of points. So we have far fewer points for the same error. Because what we were interested in here was to minimize the error on the stress intensity factors. Because the stress intensity factor is, if you remember from Paris law, the governing point with which you are solving the propagation of the cracks. So if the stress intensity factor is inaccurate, then what you get is an inaccurate propagation growth. So it's very important to have proper stress intensity factors, right? So now, how do we deal with that? If you look at the number of elements close to the crack front, you see that it's quite dense, and you would not like to have such a dense mesh everywhere, because that would be totally unfeasible. So that's what we did. Similar for surgical simulation, you want to insert a needle in a brain, if you do, or in a liver, wherever. You have localization here, clearly. You have high stresses, shear stresses and shear strains until the needle penetrates the organ and reaches the target, right? So what we did is we developed a real-time error estimate, which is able to compute in real time the approximation error, which means the ability of the numerical simulation to capture the exact solution, well, which we don't know. So this is a bit of a mathematical miracle that without knowing the exact solution, we're still able to give an approximation of what the error is. So this is something quite amazing. So we insert the needle in this virtual liver. This is work by Bui-Phuoc, and then you see the needle is inserted, the mesh is refined, and as we retract the needle, the mesh is then unrefined, because the stresses are not varying that much anymore, right? So we insert the needle, puncture, the elements are refined along the needle path according to an error estimate. It is not random refinement, as you can see also here with the boundary conditions. There is some local refinement because of error levels. Then we retract the needle, and the mesh is coming back to its original density. Okay, so that's how it looks if you insert in a brain the cannula, which is used to insert an electrode and reach a target to stimulate with an electric current pulse the target for Parkinson's, let's say, not treatment, but alleviation of difficulties. And so yeah, that's it. And now I will show you the list of papers that we published on that topic, so that you can take a better look. And I think I will end with some basics about the material point method, because I think it would be more suitable. And then in the coming days, I will be able to tell you more about the topics that we talked about today that are, in my opinion, quite important. And of course, in the meantime, feel free to tell me what you would like to talk about, and I will do my best to make it happen.